Yes. Let's start.
Happy day, everyone. This is Orekoya Olusegun, Physics Mathematics Fundamentals on YouTube. In this my YouTube, I deal with video covering exercises on physics and mathematics. But today we are taking a topic in physics, and that topic is the Doppler effect. And this Doppler effect is under what is called the sound wave. What is Doppler effect? It is an aspect of a topic in physics. Discovered by a scientist called Johann Doppler. And then the Doppler effect is, telling us the relative difference in frequency of an emitted wave, maybe light wave or sound wave, due to the relative movement between the source of the wave and the observer. Like for instance, let me say I have a source of wave. Let me say it's a sound wave. The sound wave is being emitted from this source. Like when we talk about a music blaring off from a speaker. Now, we can have a wave in this format. Around this side of the wavelength is low, but the frequency of the wave is high. The frequency of the wave is high. But around this side that I have here, the wavelength is high, but the frequency is low. Now, one thing I want us to also take note of is this. When we have a source and we have an observer here, anytime the source is moving toward the observer or the observer is moving toward the source, the frequency of the observer increases. That is case 1. Case 2, let's say I have the source, then I have the observer. Anytime that the source is moving away from the observer or the observer is moving away from the source, the frequency of the observer decreases. Another thing I want us to know is this. We know that fraction is numerator divided by denominator. This particular fraction increases when the numerator increases and the denominator decreases. This fraction decreases when the numerator decreases and the denominator increases. So these particular points, we need to take note of them while solving problem under the Doppler effect in physics. Now, another thing I want us to also take note of is this: the relationship between the frequency of the observer and the frequency of the source of the wave. Now, the frequency of observer is given as frequency of the source of the wave, times velocity of sound plus or minus velocity of observer divided by velocity of the sound wave plus or minus velocity of the velocity of the source. So this is a relationship between the frequency of the observer and the frequency of the source. Again, the frequency of the observer is given as frequency of the source times velocity of sound in air plus or minus velocity of the observer divided by velocity of sound in air plus or minus velocity of the source. So let me write the keywords in this formula here. F naught is a frequency of observer. That is F naught. Then Fs is frequency of the source, and V is velocity of sound wave, and then V naught is velocity velocity of observer, and then Vs is the velocity of the source of the sound wave. Velocity of the source of the sound wave. Now, I want us to also recall that in solving the problem here, we should have the background of the definition of a wave. As a reminder, a wave is a disturbance that travels through a medium and transfer energy from one point of the medium to the other without permanent displacement of the particle of the medium itself. Now, like I have said, when we are working on Doppler effects, I have given the relationship between the frequency of the source of the wave and the frequency of the observer of that wave. In a real life situation, if you are moving towards the speaker where the music is blaring, you will hear the sound louder. But if you move away from the source of the music, that means if you move away from the speaker, the sound will be lower. So this is, a practical illustration of what Doppler effect is all about. Now, another thing I want us to also take note of is this. The velocity of sound at a given temperature is given as a given temperature, is given as a V of sound plus 0.6 T. Now, the velocity of sound when the temperature, where Vs, when the temperature is 0, is 331. So what am I trying to say is that velocity of sound at a temperature of 0 is 331 plus 0.6 times 0, which is something as 331 meter per second. So what am I trying to say is this. The standard relationship or the velocity of sound and temperature, V, is 331 plus 0.6 T. Now, there is a problem we want to do here, and that problem is when the temperature of the air is 20 degrees Celsius. So let me start with the temperature of the air using this relationship. So the velocity we are going to work, the velocity of the air that we are going to work with at the temperature T, 20 degrees Celsius, is given as velocity of all sound wave in the air is going to be 331 plus 0.6 times 20, which is same as 331 plus 0.6 times 20, 6 times 2, that's 12. So if we add 12 to this one, we are going to have 343 meter per second. So that means the velocity of sound wave for this particular problem we are going to solve is going to be, the velocity of sound wave is going to be 343 meter per second. Now let's look at the problem here. This problem we are looking at, I'm going to create a space on the board so that we can solve the exercise. Now, look at this problem. I will read. An ambulance truck emits a sound wave with the frequency of 800 Hz. Question 1, that is question A. What is the frequency detected by a stationary observer if the ambulance truck is moving at a velocity of 30 meters per second toward the observer? Question B. What frequency will be detected if the ambulance truck is moving away from the observer? And then the condition is that the air temperature is 20 degrees Celsius. And I've already discussed what the value of the sound wave will be at a temperature of 20 degrees Celsius using this formula. And that particular velocity of sound wave will be 343 meter per second. Now, let's solve this problem. A truck emits a sound wave with frequency this. So, the truck is our source. Let me write it as S. And the frequency of that sound wave from the source is given as 800 Hz. Now, the question say what is the frequency detected by the stationary observer. Let's say this is the observer. You know, this particular source is emitting sound wave. It's emitting sound wave that is going towards this observer. So the question say what is the frequency of the observer? And observer, if the angular truck is moving at a velocity of 30 meters per second, that means the velocity of this truck is 30 meters per second towards the observer. But we are told that the observer is stationary. In physics, when an object is stationary, the velocity is 0. So that means the velocity of this observer will be 0 meters per second. Now, like I said the other time, anytime the source of the wave is going towards the observer, or the observer is moving towards the source of the sound, then the velocity here must increase. Now, because the relationship between the frequency of the observer and the source, which is the velocity of sound in air, plus or minus velocity of the observer divided by velocity of the sound in air, plus or minus velocity of the source of the sound wave. Now, when we talk about increment here, because the source is moving towards the observer, the frequency f0 must increase. So, because of the increment, we are going to take this positive side of this sign in this formula. And when we take the positive sign up, for this fraction to increase, we are going to take the negative sign down. So, this formula now will now turn to this format. V plus V0 divided by V minus V source. Now, in the parameters given concerning this question, the frequency of the observer is for Fs is 800, and the velocity of sound is what we have here, 343. So I put 343 here. Then plus velocity of the observer is 0, so that is plus 0. Then divided by 343 minus velocity of the source given is 30. So I'm going to have 800 times 343 divided by 343, take away 30, 343 minus 30. We have 3, 4 take away 3. That's 1. Then I have 313. So downward here I have a 313. So 343 take away 30, like I said, is 313 down. And then using the calculator, we are going to have 876.7 approximately as. That means the velocity of the observer is 876.7 as. If you look at this answer that we have here, compared to the velocity of the source, we can discover that the value of the frequency of the observer increases more than that of the source. So then the second question here, what frequency will be detected if the ambulance truck is moving away from the observer? If the ambulance truck is moving, this particular source is moving away from the observer. Like I said the other time, anytime the source or the observer happen to be moving away from each other, the frequency of the observer will decrease. So from the equation that we have, F0 is equal to Fs V plus or minus V0 all over V plus or minus Vs. If this particular F0 must decrease, then we are going to take this negative sign and we are going to take this positive sign. That means your denominator must increase while the numerator must decrease. Your denominator must increase while your numerator must decrease. So in a nutshell, we are going to have this equation for the second problem. V minus V0 divided by V plus Vs. Now, the frequency of the source is still 800 Hz. So we put 800 there. And then velocity of sound at that temperature of 20 degrees Celsius is 343. Using that equation I gave the other time. Then take away velocity of the observer. The observer is still stationary, 0. Then divided by velocity of a sand at temperature 20 degree is T343 for this problem, then plus velocity of the source is 30 plus 30. So this one becomes 800 times 343 divided by 343 plus 30. If we press our calculator, we are going to have 736 hours. We can see that the frequency of the observer decreases the moment the source move away. If you compare this result that we have, the frequency of the observer, if you compare it to the frequency of the source, we can see that there is a decrement. So that is the fundamental calculations under the Doppler effect. Before we go, please do not forget to like, share, subscribe, and click on notification button to have more of my video. Once again, this is a physics mathematics fundamental on YouTube by Orekoya Olusegun. Have a nice day. Bye.